NENOMATICA, where mathematics meets YouTube excellence. Welcome to this mathematics video where we'll be proving an important algebraic identity, the difference of cubes formula. Let's first understand what we're trying to prove. For all real numbers a and b, we want to show that when we multiply the difference of a and b by the sum of a squared, a times b, and b squared, we get a cubed minus b cubed. In other words, we need to prove that the product of a minus b and a squared plus ab plus b squared equals a cubed minus b cubed. Now let's start our proof. We begin with the left side of the equation, a minus b multiplied by a squared plus ab plus b squared. To expand this expression, we need to distribute the first term a minus b to each term in the second factor. First, let's distribute a minus b to each term in the second factor. This gives us a times a squared, plus a times ab, plus a times b squared, plus negative b times a squared, plus negative b times ab, plus negative b times ab, plus negative b times b squared, which simplifies to a cubed plus a squared b plus ab squared minus ba squared minus bab minus b cubed. Since multiplication is commutative, we can simplify further. This means that a squared b is the same as ba squared, and ab squared is the same as bab. So our expression becomes a cubed plus a squared b plus ab squared minus a squared b minus ab squared minus b cubed. Now let's group like terms. Notice that we have a squared b and negative a squared b. These terms cancel out. A squared b minus a squared b equals 0. Similarly, we have ab squared and negative ab squared. These also cancel out. ab squared minus ab squared equals 0. This gives us a cubed plus 0 minus b cubed, which simplifies to a cubed minus b cubed. To show the steps more clearly, let's regroup our terms in a different way. After expanding the product, we had a cubed plus a squared b plus ab squared minus a squared b minus ab squared minus b cubed. We can rearrange this as a cubed plus the term a squared b minus a squared b plus the term ab squared minus ab squared minus b cubed. We can see that the bracketed terms are equal to 0, a cubed plus 0 minus b cubed, which gives us our final result, a cubed minus b cubed. Therefore, we have proven that the product of a minus b and a squared plus ab plus b squared equals a cubed minus b cubed. In conclusion, we've proven an important algebraic identity, the difference of cubes formula. This formula states that for any real numbers a and b, the product of a minus b and a squared plus ab plus b squared equals a cubed minus b cubed. This formula is very useful in algebraic factorization problems and in calculus when simplifying expressions. Remember, the key insight was using the distributive property to expand the product, and then recognizing that certain terms cancel out. Let's summarize what we've learned. First, we stated the formula, the product of a minus b and a squared plus ab plus b squared equals a cubed minus b cubed. Next, we expanded the left side using the distributive property. Then, we simplified using the commutative property of multiplication. Finally, we grouped like terms and showed that certain terms cancel out, leaving us with a cubed minus b cubed. Let's start with our first example. We want to evaluate the expression 2x minus 3 y times 4x squared plus 6x y plus 9y squared. For the first step, we'll rewrite the expression in the standard form of a times b squared plus a times b times c plus c squared. Let's identify what a and b are in our expression. Now, let's check if the second term has the form a squared plus ab plus b squared. We have 2x squared, which is a squared. Then we have 2x times 3y, which is a times b. And finally, we have 3y squared, which is b squared. Let's verify the numerical coefficients. For the a squared term, we have 2x squared, which gives us 4x squared. For the ab term, we have 2x times 3y, which gives us 6xy. And for the b squared term, we have 3y squared, which gives us 9y squared. So we confirm that the expression matches the pattern for the difference of cubes formula. Now we can apply the difference of cubes formula, which states that a minus b times a squared plus ab plus b squared equals a cubed minus b cubed. In our case, a is 2x and b is 3y. So we get 2x cubed minus 3y cubed. Finally, let's calculate the cubes. 2x cubed equals 8x cubed. 3y cubed equals 27y cubed. So our final answer is 8x cubed minus 27y cubed. Let's move on to our second example. Here we want to evaluate the expression x minus 2 times x squared plus 2x plus 4. Just as before, we'll rewrite the expression to match the standard form of the difference of cubes formula. We need to identify what a and b are in this case. Let's check if the second term has the form a squared plus ab plus b squared. We have x squared, which is a squared. Then we have x times 2, which is a times b. And finally, we have 2 squared, which is 4, giving us b squared. Let's verify that the second term of our original expression matches this pattern. We have x squared plus 2x plus 4, which matches exactly with a squared plus ab plus b squared with equals x and b equals 2. So we confirm that this expression also matches the pattern for the difference of cubes formula. Now we can apply the difference of cubes formula again. Since there is x and b is 2, we get x cubed minus 2 cubed. Finally, let's calculate 2 cubed. 2 cubed equals 8. So our final answer is x cubed minus 8. Let's summarize what we've learned in this lesson. We've seen how to use the difference of cubes formula, which states that a minus b times a squared plus ab plus b squared equals a cubed minus b cubed. We applied this formula to solve 2 examples. First, 2x minus 3, y times 4x squared plus 6x, y plus 9y squared, which gave us 8x cubed minus 27y cubed. Second, x minus 2 times x squared plus 2x plus 4, which gave us x cubed minus 8. This pattern is very useful in algebra for simplifying expressions and factoring polynomials. Practice applying this formula to become more comfortable with algebraic special products. Now, let's look at our first example. We have the expression 2 minus 5 times the quantity for a squared plus 10, a plus 25. Let's identify our terms. In this expression, if we compare it to our general form a minus b times a squared plus ab plus b squared, we can see that it is 2a and b is 5. Now, we can apply the difference of cubes formula. Remember, the formula tells us that a minus b times a squared plus ab plus b squared equals a cubed minus b cubed. Applying this formula to our example, we get the expression 2 a cubed minus 5 cubed, which simplifies to 2 a cubed minus 125. Let's move on to our second example. We have the expression 2 a minus 3b times the quantity for a squared plus 6ab plus 9b squared. Again, let's identify our terms. If we compare this to our formula, we can see that it is 2a and b is 3b. Let's apply the difference of cubes formula again. Applying this formula, we get the expression 2 a cubed minus 3b cubed, which simplifies to 8 a cubed minus 27b cubed. Let's summarize what we've learned. The difference of cubes formula is a powerful tool in algebra that allows us to factorize expressions in the form of a cubed minus b cubed. In our examples, we've seen how to apply this formula to expressions that are already factored to find the simplified form. Remember, whenever you see an expression in the form a minus b times a squared plus ab plus b squared, you can simplify it to a cubed minus b cubed. Thank you for watching this tutorial. We need to solve the expression x minus 1/2 times the quantity x squared plus 1/2 x plus 1/4. Let's look at this problem carefully. We notice that we can use a special algebraic identity to simplify this expression. We'll rearrange the second part to match a familiar pattern. First, I'll rewrite the expression by rearranging the second factor. I'll write x squared as x to the power of 2 plus x times 1/2 plus 1/2 squared. Looking at the second factor, we can recognize that it matches the form a squared plus ab plus b squared, which comes from the pattern a plus b all squared. Now we can see that the algorithm shown in the original problem suggests that we apply the difference of cubes formula, which states that a minus b times a squared plus ab plus b squared equals a cubed minus b cubed. Finally, we calculate x cubed minus 1/2 cubed. X cubed is just x cubed, and 1/2 cubed is 1/8. So our final answer is x cubed minus 1/8. Now, let's look at our second example. This time, we need to solve the expression a squared minus 2a times the quantity a to the 4th plus 2 a cubed plus 4 squared. Let's analyze this expression. Following the same approach as our previous example, we'll try to match it to the difference of cubes formula pattern. First, let's rewrite our expression to match the pattern we need. We have a squared minus 2 as our first factor. If we look at the second factor, we need to rearrange it to match our formula. We can factor our first term as a squared minus 2a, which can be written as a times a minus 2. Wait, this approach doesn't seem to match our expected pattern. Let's go back to the original expression and try a different approach. Looking at the algorithm shown in the problem, we need to apply the difference of cubes formula directly. Looking at our expression more carefully, we can see that we need to interpret it as a squared minus 2 times a to the fourth plus 2 times a squared plus 4 squared. This aligns with the formula a minus b times a squared plus b plus b squared equals a cubed minus b cubed, where a is a squared and b is 2a. Now, we can simplify the expression. A squared cubed is a to the sixth power, and 2a cubed is 8a cubed. Let's summarize what we've learned in this lesson. We've seen how to use the difference of cubes formula to simplify algebraic expressions. This formula states that a minus b times a squared plus a b plus b squared equals a cubed minus b cubed. Let's look at our example problem. We need to simplify this expression. A minus b times a plus b times a squared minus a b plus b squared times a squared plus ab plus b squared. Let's begin our solution by grouping the terms. First, we'll group a minus b with a squared plus ab plus b squared, and a plus b with a squared minus ab plus b squared. This grouping helps us apply known algebraic identities. For our second step, we'll apply the cubic identity a minus b times a squared plus a b plus b squared equals a cubed minus b cubed. This is a well-known algebraic identity for the difference of cubes. Similarly, for our third step, we'll apply the cubic identity a plus b times a squared minus a b plus b squared equals a cubed plus b cubed. This is the identity for the sum of cubes. For our fourth step, we'll substitute these identities back into our grouped expression. We get a cubed minus b cubed times a cubed plus b cubed. For our fifth step, we'll recognize that we have a difference of squares pattern. We can apply the identity a squared minus b squared equals a plus b times a minus b. In our case, a is a cubed and b is b cubed. For our sixth step, we'll simplify the exponents. A cubed squared is a to the power of 6, and b cubed squared is b to the power of 6. So our final answer is a to the power of 6 minus b to the power of 6. Congratulations! We've successfully simplified the complex expression by following the algorithm step by step. Now, let's look at a second example that follows a similar algorithm. This time we have a minus 1 times a squared plus a plus 1 times a cubed plus 2. First, let's group terms as we did before, focusing on recognizing patterns. We'll group a minus 1 with a squared plus a plus 1 and keep a cubed plus 2 separate. For step 2, we'll apply the cubic identity to a minus 1 times a squared plus a plus 1. This equals a cubed minus 1, which is the difference of cubes formula with b equal to 1. For step 3, we'll substitute this result back into our expression. We get a cubed minus 1 times a cubed plus 2. For step 4, we'll multiply these expressions using the FOIL method. That stands for first, outer, inner, last. First, we have a cubed times a cubed, which is a to the 6th. Outer terms give us a cubed times 2, which is 2 a cubed. Inner terms give us negative 1 times a cubed, which is negative a cubed. Last terms give us negative 1 times 2, which is negative 2. Combining all these terms, we get a to the 6th plus 2 a cubed minus 2. For our final step, we'll combine like terms. We have 2 a cubed minus a cubed, which simplifies to a cubed. So our final expression is a to the 6th plus a cubed minus 2. So our final answer for the second example is a to the power of 6 plus a cubed minus 2. Excellent job! We've successfully solved another complex algebraic expression. Let's summarize what we've learned. We've seen how to simplify complex algebraic expressions by applying special product formulas. The key identities we used were the sum and difference of cubes and the difference of squares. For the first example, we found that a minus b times a plus b times a squared minus a b plus b squared times a squared plus a b plus b squared equals a to the 6th minus b to the 6th. For the second example, we found that a minus 1 times a squared plus a plus 1 times a cubed plus 2 equals a to the 6th plus a cubed minus 2. Remember that recognizing patterns and knowing these special product formulas can save you a lot of time in algebraic simplification. We need to multiply and simplify the expression 4x squared minus 6x times the expression 4x to the 4th power plus 6x cubed plus 9x squared. Looking at the first expression, 4x squared minus 6x, we can factor out a common term of 2x, which gives us 2 times 2x minus 3. Now, let's look at the formula for the difference of cubes. The formula states that a minus b times a squared plus ab plus b squared equals a cubed minus b cubed. Let's apply this formula to our expression. Now, we'll expand the expressions inside the square brackets. We have 2x squared squared, which is 4x to the 4th power. Then we have 2x squared times 3x, which is 6x cubed. Finally, we have 3x squared, which is 9x squared. Let's calculate the powers in our expression. 2x squared cubed equals 8x to the 6th power, and 3x cubed equals 27x cubed. Finally, we distribute the factor of 2 to get our final answer. 2 times 8x to the 6th power is 16x to the 6th power, and 2 times 27x cubed is 54x cubed. So our final answer is 16x to the 6th power minus 54x cubed. Now, let's move on to our second example. We need to square the expression 2x minus 1 squared times 4x squared plus 2x plus 1 squared. Let's first rewrite our expression to make it clearer. We have the square of 2x minus 1 times the square of 4x squared plus 2x plus 1. Again, we can use the difference of cubes formula. The expression a minus b times a squared plus a b plus b squared equals a cubed minus b cubed. Now we calculate the cube of 2x, which is 8x cubed, and the cube of 1, which is just 1. Now, to square this expression, we can use the formula for the square of a difference. A minus b squared equals a squared minus 2ab plus b squared. Finally, let's calculate each term. 8x cubed squared is 64x to the 6th power. 2 times 8x cubed times 1 is 16x cubed. And 1 squared is just 1. So our final answer is 64x to the 6th power minus 16x cubed plus 1. Let's summarize what we've learned in this video. We solved 2 polynomial expressions using algebraic identities. For the first example, we factored out common terms and used the difference of cubes formula to simplify the expression 4x squared minus 6x times 4x to the 4th plus 6x cubed plus 9x squared, and got the answer 16x to the 6th power minus 54x cubed. For the second example, we used the difference of cubes formula and the square of a difference formula to simplify the expression 2x minus 1 squared times 4x squared plus 2x plus 1 squared, and got the answer 64x to the 6th power minus 16x cubed plus 1. Remember to always identify the appropriate algebraic identities that can be applied to simplify complex expressions. Practice these techniques with similar problems to strengthen your understanding. We need to simplify the expression x times open parenthesis 1 minus x close parenthesis times open parenthesis 1 plus x close parenthesis times open parenthesis x squared plus x to the 6th plus x to the 4th close parenthesis. Let's start by rearranging this expression to make it easier to work with. First, we'll group the factors to highlight the structure of the expression. Now, we'll apply the difference of squares identity to simplify open parenthesis 1 minus x close parenthesis times open parenthesis 1 plus x close parenthesis. This gives us 1 minus x squared. Next, let's rearrange the terms in the third factor to put the powers in ascending order, which will make our next steps clearer. So we have x squared plus x to the 4th plus x to the 6th. Now, we can see that we have 2 special forms to work with. First, x minus x cubed can be factored as x times open parenthesis 1 minus x squared close parenthesis. And looking at the second factor, we can recognize the pattern as squared plus ab plus b squared, which is related to the identity a cubed minus b cubed equals open parenthesis a minus b close parenthesis times open parenthesis a squared plus b squared close parenthesis. Therefore, we can simplify this to x cubed to the power of 1 minus x cubed to the power of 3, which equals x cubed minus x to the 9th. Now, let's look at our second example. We need to simplify the expression open parenthesis, y plus 2 close parenthesis times open parenthesis, y minus 2 close parenthesis times open parenthesis 2, y to the fourth plus 32 plus 8, y squared close parenthesis. Let's start by applying the difference of squares identity to simplify open parenthesis, y plus 2 close parenthesis times open parenthesis, y minus 2 close parenthesis. This gives us y squared minus 4. Next, let's factor out the common factor of 2 from the second factor. This gives us y squared minus 4 times 2 times open parenthesis y to the fourth plus 16 plus 4, y squared close parenthesis. Let's rearrange the terms in the third factor to better see the pattern. We get y to the fourth plus 4. Let's start with our example. We need to simplify the following expression. A squared minus b squared times a to the fourth plus b to the fourth plus a squared b squared times a to the sixth plus b to the sixth times a to the 24th plus a to the 12th b to the 12th plus b to the 24th. Our first step is to rewrite the expression to make it easier to work with. Looking at the second term, we can rearrange it as a to the fourth plus a squared b squared plus b to the fourth. This doesn't change the value, but helps us recognize a pattern. Now, we notice that we can apply a well-known formula, the difference of cubes. The formula states that a minus b times a squared plus ab plus b squared equals a cubed minus b cubed. We can apply this to the first two factors. Let's simplify the expression further by calculating the powers. A squared cubed equals a to the sixth. Similarly, b squared cubed equals b to the sixth. So our expression becomes a to the sixth minus b to the sixth times a to the sixth plus b to the sixth times a to the 24th plus a to the 12th, b to the 12th plus b to the 24th. Next, we notice that the first two factors form a difference of squares pattern. A to the sixth minus b to the sixth times a to the sixth plus b to the sixth. Using the difference of squares formula, a minus b times a plus b equals a squared minus b squared. We can simplify this to a to the 12th minus b to the 12th. Now we can apply the difference of cubes formula again. Notice that a to the 12th minus b to the 12th times a to the 24th plus a to the 12th, b to the 12th plus b to the 24th follows the pattern of the difference of cubes formula again. So we'll highlight this pattern again. Finally, we simplify the powers in our expression. A to the 12th cubed equals a to the 36. B to the 12th cubed equals b to the 36. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.